Good afternoon, everyone. I'm going to go ahead and get us started here in the interest of time. I'd like to welcome everyone to the next installment of the Interface Engineering High Performance Buildings webinar series. My name is Kevin Cahill. I'm a principal here in our Washington, D.C. office. I appreciate you all taking time out of your day to join us today. Hopefully you're all staying healthy and happy, working from home, and as we work through these interesting times. This is the fourth webinar in this series that Interface Engineering has been doing, and we will continue to have these alternating weeks every other week as we move forward. I'd like to take an opportunity just to introduce our speakers today. Today we have Joe Daino from Interface Engineering. Joe is an associate principal here at Interface Engineering. He has his master's degree in architectural engineering from Penn State University. In addition to being our mechanical discipline lead here in Washington, D.C. office, Joe serves on a 3-member internal corporate technical committee for mechanical, and they work on things from process to standards to quality control, and lately providing detailed consulting services on how to protect buildings from the virus situation we are facing, and he'll get into that today. Also presenting today is Roger Frechette. Roger Frechette is a principal in our Washington, D.C. office. Roger is a managing principal and board member here at Interface Engineering, and those two groups provide corporate governance and policy for the company. As you can imagine, those two tasks these days with COVID and working from home keeps him quite busy. The topic today is building design responses to mitigate COVID-19 virus threat. Joe and Roger have spent a lot of time on this issue, both from a company standpoint internally, as well as on the design consulting side with our clients, providing some good advice to current designs as well as existing buildings. So with that, I will turn it over to Roger Frechette, and he'll take you through today's presentation.
Well, thank you, Kevin. And I'd like to thank everybody for inviting us into your living room and into your home offices today to go through this, what we think is a very important topic matter. But just very quickly, I'd like to talk about our course description today. So today we are talking about specifically about what you may want to consider doing differently in terms of design with respect to new and existing buildings to protect it from the SARS-CoV-2 virus. And that is the virus, of course, that causes the COVID-19 disease. So today we're going to be talking a little bit about design strategies. We're going to be talking about different ways to operate existing equipment. And we're going to talk about an array of things that we can be doing differently moving forward, knowing that we have this new threat that we are all facing. So the learning objectives in today's discussion, one is to gain a better understanding of how the SARS-CoV virus can spread within an occupied building and the different types of human exposure which can lead to infection. Secondly, to discuss specific design strategies, technologies, and componentry which can provide protection and reduce the risk of virus infections in both new and existing buildings. Thirdly, we're going to learn about how automatic controls within a building's management system can be altered and reprogrammed with different sequences of operation, which can reduce the risk of human infection. And lastly, we're going to learn the relationship between the infectious disease mitigation strategies, energy efficiency, and sustainability, and discuss how building maintenance policies and procedures will likely change as a result of the current pandemic. So before we get into it, just a quick discussion about the virus itself and how it spreads. And I've numbered these 1, 2, 3, 4 in this order for a particular reason, because they really are in the order that we believe is the highest risk to lowest risk. So direct contact with another human being, touching, sharing bodily fluids. This is by far the #1 way that the virus can be contracted. Secondly, the indirect contact, and that is touching something that somebody else had just touched. Again, still shedding or sharing the virus through the moisture on that from that individual's hands. Thirdly is what I'm calling close contact, and this is the social distancing that we're talking about. This is the exhaling of air and the associated water droplets and their ability to carry some distance through the air and being inhaled and exposed to the mucous membrane of others that might be in the same room. And fourthly, and the one that is going to get a lot of attention today, and that is how our buildings' air conditioning and mechanical systems can help to convey and move the virus from one point to another. So although there's going to be a lot of discussion over number 4 today, it is in fact the lowest risk of the 4 different ways that the virus can potentially be contracted. So the keys to the mitigation, we've taken a lot of different ideas and strategies and recommendations from health professionals and recommendation from industry professionals, and we've put them into 5 different categories. And we call it remove, neutralize, dilute, divert, and defend. So these are the 5 key strategies to be able to deal with mitigating the threat. So before we get again into the specific strategies, just a little bit about the virology of the coronavirus so that we can understand specifically what we're dealing with. On the left-hand side, those little black circles roughly represent the diameter of various elements. So the big black circle there is 150 microns in diameter, which is the average diameter of a human hair. And as you go down, the elements get smaller and smaller. Viruses are extremely small. So in the lower right-hand corner, that is the coronavirus. So the average diameter of a coronavirus spore is 0.006 microns. Now, one thing that is very important in this discussion, and it's very good news for all of us, is that the COVID-19 coronavirus is not technically an airborne virus, meaning these small particles do not have the ability to travel through the air on their own and stay alive and have the ability to infect others. However, they can survive within droplets of water, and droplets of water can be large and they can be small. And at their smallest size, we generally refer to as an aerosol. They form very small droplets called droplet nuclei. And these droplet nuclei can, in fact, carry the virus through the air. And this droplet nuclei is very, very small in itself. Not nearly as small or as tiny as the coronavirus, but it can be 1 to 3 microns in diameter. So again, looking back on the chart at the left, that's similar to the width of a element of sort of bacteria or tobacco or cooking smoke. That's the size that we're needing to deal with. Now, when we compare the coronavirus to other diseases that we've seen in the past, what the bad part about the coronavirus is, again, it can survive in the smallest droplet nuclei. That was not the case with the Ebola virus. The Ebola virus really, it could survive in large droplets of, say, 100 nanometers, but when you get to the smallest size droplet nuclei, it did not survive. So if you stayed good distance away from a patient who had Ebola virus, chances are you would not get infected. However, when you talk about the coronavirus, these droplet nuclei, we've heard about the social distancing of 6 feet, but the reality of it is this droplet nuclei can carry much further. It can carry up to 10 meters or roughly 30 feet. Now, the risk of coming in contact with it obviously goes way down just because of the way that it's spread over the same amount of area, but it is possible for this virus to carry a longer distance than I think many people believe. So one bit of evidence of this came from a study that was done, and it's been in the news quite a bit, and I believe there's a Newsweek article on it. But it was a study done about a restaurant in the city of Guangzhou, China. And what happened, if you look at the lower left-hand corner, there's a little yellow circle with an A1. There was a person who went into a restaurant who was infected with the virus. And they were sitting at a table, and other individuals sitting at that same table and at some adjacent tables were clearly further than 6 feet away. But 9 other individuals were infected. And the interesting thing about the study is that it doesn't show the greater layout of the restaurant, but there were 71 other individuals in the same restaurant who did not get infected, including all of the staff. So the conclusion that was drawn from this study is it was actually the air conditioning unit that was directly blowing on these 3 tables that was drawing air back from that small area, that small zone, and redistributing that air to that same zone that was a primary culprit in the dispersion of these droplet nuclei, and certainly aided in the infection of the individuals in its direct path. So this then leads into some of the highlights that we're going to talk about today, and it touches on multiple categories. It talks about the need to try to remove these droplet nuclei from the airstream. It talks about to the benefit of dilution, and you know, there's a saying that has been used in the world of HVAC for a long time, and that is dilution is the solution to pollution. We've always talked about diluting airstreams to reduce airborne contaminants, and that is certainly true when you talk about air that contains these droplet nuclei. And then lastly, the benefits of diverting that airstream. So we'll touch on all of those as we go through this presentation. So the first category of removing, obviously one of the best things that we can do is take the virus from the airstream so that it does not come in contact with humans. And I put this chart in here to demonstrate the challenge that we have. A lot of people say, well, you know, our building has a good HVAC system, it's modern, it has air filters, so we should be good. And I guess the message I have today is don't be so sure. That may not be the case. And here's the reason. When you talk about, say, a wall-mounted air conditioning unit, similar to the one that I just showed in that restaurant in Guangzhou, they tend to have a very small, cheap, and throwaway type filters. And these filters might do a good job filtering out things like dust mites and pollen. However, if you look at the column on the left-hand side, and this is from ASHRAE standard 52.2, we're really focusing on that column that says 1 to 3 nanometers, because again, this is the width or the diameter of these droplet nuclei that we're concerned about. A MERV3 filter is not going to stop it at all. It's just going to pass right through, and that's exactly what that study had concluded. It helped to the distribution of the water of droplet nuclei, and did nothing to stop it and keep it from being redistributed. Fortunately, most of our buildings do better than MERV3 filters. Although if you were to tour a bunch of office buildings in the greater Washington, D.C. area, you'd probably find the most common filter in buildings' HVAC systems is this one here, a MERV8 filter, which is still a pleated type filter with throwaway synthetic media. And these again are better. They will remove mold spores, dust mites, hairspray. You know, they do a good job taking larger particles of the air. But again, going back to that 1 to 3 nanometer column, these are not going to protect from having that droplet nuclei be redistributed to the space. The primary organization for HVAC engineers is called ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. They have put together an emergency task force to deal with the pandemic and have come up with a series of recommendations. And one of them is that wherever possible, to remove these MERV8 filters and put in place at least a MERV13 filter. And a MERV13 filter will remove more than 90% of those water droplets and other contaminants of that same diameter. If you can do better than a MERV13, it's great, but a MERV13 is really where you need to get to be able to start to block the passage of elements of that size. Now, as you go from the bottom to the top, the reason everybody doesn't use these filters is as you go up, the filters get more expensive. They get larger. So you can't necessarily take out one and just slide in another. There's a frame size with an existing mechanical equipment, and you either need to put the best filter in you can for that frame size, or now you're reconfiguring your mechanical equipment and altering it to accept better filters. The other thing that happens is there's a pressure drop. It takes a greater force to drive the air through these filters as you go from bottom to top here. So a MERV 13 filter requires more fan energy to pull the air through the filter. And this obviously has a negative impact on the energy performance of the building. And you might note as we go through the different items today that there is almost a reverse relationship between some of these strategies and what you would do to make a building more energy efficient. A lot of the ideas, a lot of the suggestions here will increase the amount of energy the building consumes. So a key aspect of all of it is flexibility. We want the ability to make changes to deal with the high risk that we're dealing with now, but have the ability to revert back to a condition where perhaps we have less filtration capability, but better energy efficiency when the risk drops back down, which it will. Now, removing 90 to 95% of these particles is a recommendation, and I think sufficient for most buildings. However, if you have a critical facility, if you had a nursing home or a hospital or clinic, you may want to go up to a MERV 18 filter, and this is what they call HEPA filters, and they can remove up to 99.99% of the particles of this particular size. Expensive, very heavy pressure drops, but depending upon the facility that you have, you may need to take that final step up to the better filter. Joe, do you want to jump in?
Sure, absolutely. Thank you, Roger. As an alternative to what we refer to as the mechanical filtration that Roger was just talking about, there are other options out there. One that is gaining some popularity in the current environment is what is known as electronic filtration. Oftentimes this will be referred to also as electrostatic filtration, or the concept of an electrostatic filter. But it's important to note that not all electrostatic filters are actually electrified. Some of them are these metal washable type filters that do not use electricity, but still create some sort of static electricity to help capture particles. But these are not quite as efficient at trapping dust and particles as electronic filtration is. And essentially what an electronic filter is doing is it's polarizing both the filter media and the particles which are traveling through the filter media. And those particles are then drawn in to the individual fibers of the media. And why that is important in the application of electronic filtration is it allows for the actual media fiber to capture particles on 360 degrees of each fiber. So everyone's probably familiar with their air filter at home. 3 to 6 months pass by, you forget to replace it, you go to pull it out. When you pull it out, the side that's facing the airstream tends to be very dirty. But when you look at the back of the filter, it tends to be relatively clean. That's because the particles are actually only being captured on the front side of the media. Electronic filtration actually allows all of the media to essentially capture these particles, which dramatically increases the effectiveness. And what that also does is reduce the pressure drop within the filter media itself. So that's one of the reasons that these have become a very popular option, not only in new equipment, but in existing equipment. So if you have existing equipment that, to Roger's point, cannot handle HEPA filtration or even potentially MERV 13 or 14 filtration, electronic filtration can offer an option at a lower static pressure to essentially achieve the same effectiveness. The other major reason that people have been looking into this is because many of the manufacturers claim, and it has been substantiated, that the maintenance requirements are substantially reduced. Because they're low pressure drop and because they have the 360 degree collection on each fiber, manufacturers claim maintenance cycles that are in excess of 3 years. And there's actually a well-documented study. This type of technology was utilized in ASHRAE's headquarters in Atlanta, and they actually went 7 years and 4 months before they actually replaced their filter media. So from a maintenance standpoint, that allows the maintenance staff to focus on other things rather than having to do excessive amounts of filter changes. From an electrical standpoint, they're relatively low power usage. They're typically almost always low voltage systems, so say 24 volts. And because of the low static pressure drop requirements, they can be utilized in a range of equipment. So small equipment down to fan coil units, fan power boxes, things of that nature, small rooftops, but also can be scaled up, as you can see in the image on the left, to very, very large air handling systems. Roger, I'll throw it back to you.
Yeah. Sorry, that PowerPoint's moving a little slow today. Okay, so now it's sort of jumping categories to the category of neutralization. You know, if you can't physically remove the particle from the airstream, perhaps the next the best thing is neutralization. And you know, bacteria is a living organism. Essentially, it has DNA to it, and you know, we have technologies that, like UV light, that can actually break down the DNA. They can destroy the DNA and keep that bacteria from reproducing. And ultraviolet has been a strategy used for killing bacteria for quite some time. Viruses are a little bit different. They don't have a DNA strand. They have what's called an RNA strand, but viruses can be neutralized using UV technology in the same way. You can break down the bonds that hold the RNA strands together and essentially prevent reproduction of the virus, in essence, killing it. But before we get into a discussion of specifically how, I wanted to talk a little bit more generally about UV light, because I think there's a lot of misconceptions about UV light and how it works and when it works and what it does, and just getting into that, starting with what is UV light. UV light is essentially radiation, and there's all kinds of radiation all around us, ranging from radio waves to microwaves to visible light to ultraviolet light, etc. All of these are forms of radiation, and the only thing that really makes them different is the wavelength. You know, they all travel in waves, and depending upon the distance between the waves determines what kind of radiation it is. Radio waves are quite harmless. They have very long wavelengths. Microwaves a little bit more dangerous. But when you get to ultraviolet light, it can become dangerous. And just a drill down on ultraviolet light, the range of wavelengths of ultraviolet light range from about 180 nanometers up to about 400 nanometers. So they've further broken down ultraviolet light into 3 categories: UVA, UVB, and UVC. UVA light is, you might know as like black light that you know, we used to shine on our velvet Elvis posters back in the 70s. That's an example of UVA. UVB is a little bit more harmful, and it can penetrate. The wavelength is such that it can penetrate the skin and give us a suntan or a sunburn. And UVC is much more dangerous than even that. And UVC is where the focus of this discussion is going to go. Now, I've heard a lot of people say that, you know, they've had a package delivered to their house and it's been sitting on their doorstep in direct sunlight. Therefore, it's been sanitized because of the UV light. That is not necessarily true. Now, your package might get very warm sitting in the sun, and the heat might potentially kill the virus. But the reality of it is, if you look at this chart right here, when you talk about UVA, only about 5% of UVA radiation is absorbed by the ozone layer, but it's pretty harmless to the human body. The UVB And again, that's the UV that gives us the sunburn. 95% of it is absorbed by the ozone layer, but it's that 5% that manages to get through that can give us that bad burn. UVC radiation, 100% of it is absorbed by the ozone layer. So really, UVC directly from the sun does not exist on Earth. So the UV lamps that provide UVC light are really man-made, and there's lots of examples of them. So this shows that wavelength of the UVC, and that light blue curve there represents the effectiveness of UVC light. So even UVC light can be very, very effective at a very particular wavelength, and 265 nanometers it's when it's at its greatest effectiveness. And if you were to dial that wavelength down even to 200 nanometers, it's only 10% as effective as it could be at 265 nanometers. So there are new light fixtures out there that are LED UVC lights that can be tuned specifically to 265 nanometers at their greatest effectiveness. However, they're very expensive and they're not really universally available in the marketplace just yet. So predominantly the UVC lamps that you see for germicidal irradiation are low pressure mercury lamps, and they're not at that absolute best wavelength, but they're pretty close at 254 nanometers. They're about 85% of what you could potentially get out of UVC light in terms of effectiveness as a germicidal element. So UV, there's really two basic types of UV light. The first is surface light, and this can be used on equipment for disinfection, for area sterilization, and for microbial growth. So this is an equipment, this is an example of equipment disinfection, and they're doing this in China right now. At night, when you're not using your buses, they have these storage bays where they roll the bus in and turn the lights on and leave it on for at least a half hour to an hour, which does a fantastic job of killing all of the bacteria and viruses that may have been in that bus. Problem is you cannot have a person in here, and that is because this UVC radiation can be very damaging to the skin. It can be very damaging to the eyes. So it's very important that the technology be managed appropriately. But it does take perhaps at least 20 minutes to a half hour for this to be in direct UV light to properly kill the virus. A second use of this technology, and this is what we call area sterilization, is used in hospitals. So if you have a treatment room or if you had an operating room, between patients, they would roll in one of these UVGI lamps, and again, let it run for 20 minutes, a half hour, and that is generally sufficient time to zap the RNA strands for all of the potential viruses, or DNA strands for all the bacteria that may have been left behind from the previous patient. But once again, humans cannot be in the room while this is running. The third example, these lights are used in air handling units for a similar purpose. They can be shined on the upstream face of air filters, or even more commonly on the wet side of coils, or the downstream side of cooling coils. The downstream side of a cooling coil is called the wet side. That's where the air hits a saturation point. There's a lot of moisture and potential for mold growth. So these devices have been used for many years to kill the mold, to keep the coils clean. So it's good for indoor air quality, but it also burns this bacteria off the face of the coil, so it keeps the efficiency of the coil at its maximum potential. So the second category is a little bit more difficult, but it's called AIRSTREAM neutralization. And you can find this in HVAC units and ductwork, or technology that's called upper room irradiation. So this image on the right-hand side is actually showing both. It's showing the surface conditioning of the wet side of a coil, but it's also showing an induct airstream UV lamp that is attempting to kill the virus as it passes through the airstream. And here's a close-up of what one of those devices look like. They can literally be cut into a section of ductwork, perhaps a little bit more effective on the return ductwork from the supply because of the air temperature and because of the potential concentration of the virus on the return compared to the supply. Now, I put this diagram together to represent one of the challenges of putting these elements in an HVAC air duct. So I've just picked a duct here, 84 inches by 32 inches. And I've suggested that you get air flowing through that duct and that we add UV lamps. And what's important is you want a good straight length of duct before and after of the UV lamps. And in this case, I'm showing 8 feet. So if the airflow were at about 500 feet per minute, which is what you might find in an air handling unit, that would be about 8 feet per second. So if I had 8 feet of run, that means your irradiation zone is 1 second, meaning if there's a particle flowing through that purple zone, it is going to be irradiated for a time period of 1 second. So irradiance is the dose of energy, and it's measured in power watts times time, measured in seconds, divided by meters squared. So the longer the period of time you can radiate that element, the better the chance that you have to kill it. Because it's moving so fast, unlike surface irradiation, that you're essentially aiming the light on it directly for a period of time, you need a much higher level of irradiance, a much higher level of radiation, a bigger dose to kill that is passing through in such a short period of time. The problem in ductwork is major ductwork in mechanical systems usually is not designed for low velocities like 500 feet per minute. They usually run at anywhere between 1,500 and 2,500 feet per minute. So to make this work in an air handling unit is difficult because you would be adding 8 feet of length onto your air handling unit. To make it work in ductwork is very difficult because you would really need to flange out your ductwork at some point to a much larger cross section to lower the velocity to give you the ability to kill the virus, which most people don't do either. So what they do is they compromise and they say, okay, well, maybe it takes 4 passes or 5 passes through the mechanical system before that light might kill the virus. So where that really brings you to is the fact that not one of these strategies is going to definitely kill the virus, and sometimes it takes several strategies working in concert to be able to give you the greatest reduction in risk. In fact, there was a report done by a gentleman by the name, I can't pronounce his first name, but by Dr. Kowalski, who studied airborne infection control in hospitals. And in his study, he looked at all different kinds of pathogens and microbes, and they all react slightly different. Some are more stubborn than others. But when he combined 2 strategies, a MERV 15 filter with UV technology with a URV rating of 15 for coronavirus. Now, this was not the COVID-19 coronavirus, but it's similar. This was the SARS coronavirus. They were able to achieve nearly a 70% kill rate or disinfection rate, but it did take both technologies working in concert to be able to do that amount of work. And then the last strategy that has to do with dealing with the airflow is what's called upper room, a UVGI. So the notion here is as the air is coming out of your supply air diffusers or is returning to your return air diffusers, you can mount this equipment on the wall. It has blades so that the rays of the UV light are not directed at humans, protecting their skin and their eyes, but is directed really at the ceiling. And you might find these in treatment rooms, you might find them in hospitals, in waiting rooms. Generally do not find these in hospitals. I think there is a risk. You could imagine someone not understanding what this is, climbing up a ladder and staring at it for a few minutes and damaging themselves. But it is a technology available in the marketplace. And this is my buyers beware slide. There's a lot of different things coming on in the marketplace, and I've seen examples of these UV vestibules that you can walk through that will help disinfect, or even lights that plug into your cell phone that you can shine on your iPad or your laptop. The reality of it is you either have a dosage that is so low that it's not going to hurt your skin and your eyes. At that dosage, it's probably doing little to nothing to hurt the virus either. Or you have a dosage that's much higher and is effective on the virus, but is damaging to humans. So a lot of these devices, they're saying, hey, they're UV, they can help with the virus. And the reality of it is, yes, if you took a wand and you put it on top of your laptop and let it shine for 20 minutes, you would probably kill the virus on your keypad. But would you really do that is the question. So just know that not all UV is created equal. And then this is even one other example. This is a representative image. It's not a real technology. It has not been approved by OSHA, but there's a notion that if you used UV at a different wavelength of 220 nanometers wavelength, that you could put a permanent installation that would give a continuous, never-ending dose of UV to the occupants. But again, I think that long-term exposure to UV to humans is not a good thing, and I would be surprised if any time in the near future we see approved products for this kind of application. But it is something that is being thought of and researched. Hey, Joe.
So Roger touched pretty extensively on some of the UV and UVGI technologies, and I wanted to just take a moment to talk about two other technologies that are out there. Potentially people may have started hearing these words come up, and so I wanted to spend a little bit of time to explain what they are, what they do, and why they would be useful. The first is what is known as photocatalytic oxidation. The name is complicated, and the technology is actually somewhat simple. It's still based on the utilization of ultraviolet light, but what this air purification technology does, and just to differentiate, when we're talking about UV or photocatalytic oxidation, we're talking about air purification, not just passive filtering. In most cases, these systems are not a replacement for filters. They are something that we add in addition to. So photocatalytic oxidation essentially works by shining an ultraviolet light onto a catalyst, in this case titanium dioxide, and you produce what are known as hydroxyl radicals. And these are important because that is what's going to actually seek out and attack volatile organic compounds, bacteria, viruses, etc. And effectively what they're doing is damaging and destroying the cells of bacteria and viruses and creating a byproduct, which is essentially water vapor and carbon dioxide. And so the technology, I like to think of this as more of an offensive than defensive technology, where you're really getting out there and trying to attack the viral components or bacteria or whatever the specific VOC is that you're trying to attack. This is a technology that would typically be placed upstream of a traditional filter, because again, you're attacking these viruses, but to actually remove them from the airstream, you still need some sort of filtration. And really, like I mentioned, this is moving from a filtration to an air purification type technology. The next topic that I wanted to talk about, Roger, if you could advance the slide, is what's known as bipolar ionization. It works in a similar way to photocatalytic oxidation, but there are a couple differences. So essentially what this is doing is creating positive and negative oxygen ions through these ionization tubes, which again then will attack VOCs, bacteria, viruses, and essentially render them inert. Specific to how they deal with viruses. The image on the bottom right essentially shows, what would be a coronavirus type molecule. Again, it's worth pointing out that the current coronavirus is so new that no one knows, with 100% certainty how these systems are going to work. The best we can do is to compare it to other coronaviruses from the past, H1N1, SARS, MERS, and see how those viruses reacted to these as sort of a parallel. But essentially what happens is you have these positive, negative ions, and they will attach to the proteins from the membrane of the virus, so not actually the virus itself. And what ends up happening is that these ions essentially steal a hydrogen and leave holes in the membrane. And once the membrane of the virus is compromised, it's essentially been inactivated, such that even if the virus entered your body, because it's unable to attach itself to a cell, it actually can't cause infection. The really unique, in my view, the really unique thing about bipolar ionization is that it's something that you actually put in the supply airstream. So almost all of the other technologies that we've been looking at are something that are placed in the return, let's say, of an air handling unit. And so what that necessitates is that you have to bring whatever you're trying to eliminate back to a single point to deal with it. Bipolar ionization can be put in the supply airstream, where you are actually sending out these activated oxygen ions into the space. And so it can be another offensive tool if you have a specific area of concern to utilize a technology such as this. So if you go to the next slide, Roger, we can show some examples of what these systems look like. So you can see in both images the tubes. Those are the ionization tubes. Those would be placed inside an air handler or inside of a duct. They do have a fairly large capacity. So the image on the left is an 8-tube system, which would actually be appropriate for an approximately 16,000 CFM system. And again, there are a lot of variables that go into how effective these are and how you design them. Their location in the unit, the velocity of the air that's passing, all of these impact the amount of time that the ionization can occur, and so how much you can produce and how effective it's going to be. So it is very critical that these are designed systems. I know that there's been a lot of talk about, simply taking one of these and buying it and putting it in a system, sort of without doing the scientific sort of rigorous background to figure out if you're actually accomplishing something or not. So it's very important to know that each individual application of a system like this is going to have to be designed. And finally, this image sort of shows what does this look like, right? So if I'm installing this in a piece of equipment, such as the image on the left, which shows a bipolar ionization array, and that's substantially more than the 8 tubes. You can put several of these systems sort of in parallel to increase the effectiveness, or if you have a much, much larger airstream, multiple units can be placed side by side inside a unit. The image in the center is something that has been applied to a smaller air handling unit where there is not space inside the unit itself for the equipment, so it's been mounted in the supply air ductwork stream. And the image on the right is something that is utilized when you're not looking at a system-wide application of bipolar ionization, but perhaps you have one specific room that is part of a greater system that has sort of a greater need or a greater concern. You can mount these directly in the duct with much smaller, essentially bipolar ionization tubes, and address specific spaces. So now we're going to move into a new section, which we're calling dilute. Roger had mentioned it before that, it's been a long-standing application within the HVAC industry. That dilution is oftentimes, one of the most effective things that you can do. And the reason is that, as you continuously recirculate air within a space and you do not introduce more outside air, you're really relying very, very heavily on your filtration system or your air purification system to handle VOCs, bacteria, viruses, etc. The idea of additional dilution air is that as much as is practical, when you can bring in additional outside air, you're essentially displacing all of those harmful contaminants that might be in the airstream. And so what we're looking at on the screen now is, what I would consider to be a traditional recirculating VAV type system, where you have outdoor air coming in, mixing with some quantity of return air, and then being cooled and supplied to the space by the supply fan. And so one of the things that this gets into the sort of the controls changes and how we have to look at our existing systems and systems that we're designing now a little bit differently. And also to Roger's point about the energy usage, we are definitely recommending to do things that will have a negative impact on overall energy performance, but a very, very positive impact on indoor air quality. And so the idea is, to the greatest extent possible, to provide as much outside air into the building as possible. So as long as the cooling coil can keep up, essentially the recommendation is that you have that outside air damper 100% open, and that you're relieving 100% of the air from the space out of the building without doing any mixing. This requires a little bit of a modification to what we would see as our traditional control sequences to allow for 100% outside air, because essentially you have to reprogram the system to only start to modulate that 100% outside air damper down when you can no longer reach your dry bulb or wet bulb set points. So there's implications for energy, but again, the key is flexibility. We know that in the future, hopefully, we will not have to operate our systems like this 100% of the time, but designing in the ability when it is necessary to operate the systems in this way is really key. So dedicated outside air systems is another sort of dilution methodology. These have become very, very common. We design many systems that utilize the dedicated outside air systems, or DOAS systems. And really the impetus behind doing these types of systems is to decouple the ventilation load from what is the sensible cooling building load. And so a DOAS unit allows us to precondition all of the outside air before we're bringing it into a specific space. So inherently, they're pretty good because they're always 100% outside air. There is no real recirculation mode of operation for a DOAS unit. But more often than not, when you're utilizing a DOAS unit, it's going to have some sort of energy recovery device. Because again, since we're not recirculating that air, we want to extract as much energy out of the exhaust air stream as possible. And so oftentimes you'll see an enthalpy wheel or a desiccant wheel, as shown on this image here. Now, there is some concern that operating an enthalpy wheel or a desiccant wheel is going to create a scenario where you're transferring or you have crossover of potential contaminants. So again, the recommendation here is that you bypass that wheel. So if the unit is large enough, you can actually open the bypass dampers so that the wheel is not being utilized. Or if you don't have the bypass dampers, you're actually just stopping the rotation of the wheel to eliminate any crossover to the greatest extent as possible. Some other controls changes that are associated with both this type and the other type are demand controlled ventilation. We've been doing that for some time to reduce outside airflows, but the recommendation now is that we do not allow those outside airflows to be reduced no matter what the CO2 level is in space, because again, we want to do as much dilution ventilation as possible. And the idea that we would be doing a ventilation flush as part of the morning warm up or cool down to essentially bring as much outside air through the building before occupants enter as possible. Okay. So now we're going to get into what we call divert. So the diversion schemes, the first one, if you advance to the next slide. Yeah, building pressurization and compartmentalization. This is something that has been used effectively in the healthcare industry for decades. Obviously, in a healthcare application, you have specific spaces in a building which are very critical and need to be separated. And I think some of that methodology is going to now sort of flip over into our other building types, even looking at hotels, multifamily residential, and even to some extent office buildings. So for a dwelling unit type application, the idea is that we need to increase the amount of positive pressurization in the corridor so that all of the individual dwelling units or hotel rooms are essentially better isolated. What we're really trying to avoid is spread from one space that isn't recirculating with another to that space. And I wanted to highlight this because this is something that's sort of up and coming, probably not on everyone's radar, but it is something that's being looked at. This is what I would consider to be more of an experimental technology that's being studied now, but they're known as personalized ventilation systems. And as you can see with the name and the images that are included here, it is exactly that. It is a ventilation system that is meant for a specific individual in what I would consider to be a very sort of rigid, precise setting. But what it does is it allows to very, very precisely control the air quality that's being delivered to an individual's breathing zone. Obviously, in an application like this, there are a lot of variables that one would need to account for. It requires an extremely controlled environment, but we really just wanted to show this because, you know, these are the types of things that people are looking at for when you have a controlled environment, such as, you know, an enclosed office or potentially a laboratory type application where a person is seated for some period of time. These systems have been shown to be extremely effective.
All right, well, I'll jump back in. So all of these suggestions and ideas and technologies really talk to the equipment, the machines within our buildings. And one thing that we don't want to lose track of is the most important machine in this equation is the human body. And you know, one thing that we have learned about this particular virus is that some individuals have immune systems that seem to deal very well when infected, and other people they haven't fared as well. So our body and our body's immune system becomes a very important element of this equation. So when we get into the building itself, and this is beyond just upgrades to buildings' mechanical systems, there's a lot of things that people are considering right now. For our own office, we're looking at putting signage around the building to remind people to wash their hands and keep their social distancing and keep the gathering of people as low as we can, you know, to help prevent the spread. Humidification of the space is important, and then there's been a lot about this topic, and there's always been discussion about once the summer hits and it's more humid outside that the virus will go away. I think the reality of it is the virus doesn't go anywhere, but one thing that happens within the human body when the body is warmer and the humidity levels are higher, it somehow enhances the human immune system and gives humans a better chance at sort of fighting off the virus. You know, they don't know exactly why yet, but humidity within spaces is something that we're also going to want to consider. And then daylight. And again, I mentioned before, the sun is not going to give the UV radiation, you know, to kill the virus. But what the sun does give us is vitamin D. And that's that UVB and UVA light that we talked about. And that vitamin D to the human body is important because it's one of the elements that helps to boost, again, the human immune system. So natural light is very important. I think we'll see a lot of changes in the devices that we use within buildings to prevent the touching, that number 2 way of contracting the virus. So touchless soap dispensers, faucets, door openers, hand sanitizers, hand dryers. If I had a couple of dollars to invest, I would probably look at companies that manufacture those. I think they're going to do a lot of business. And then focusing on just the health of the work environment itself, you know, we suggest considering providing relaxation rooms, reducing stress boosts the human immune system. That'll be helpful. Looking at what you eat, and if for the architects in the crowd that are familiar with the WELL certification system, they've been talking about these suggestions for a long time. Consider get rid of that vending machine with the carbonated sugar sodas and snacks, and replacing it with bowls of fruit. Fruit, particularly citrus fruits, are very helpful. They're loaded with vitamin C, and they're loaded with vitamin C, and vitamin C is known to boost the immune system. And also certain nuts, almonds particularly, have a lot of vitamin E, and they're filled with antioxidants, and those can be very helpful to the immune system. Providing standing desks, again, for good cardiac health, helps with the immune system. And then I know for a fact Joe Diano has his plants at the office, but having plants at your office, they give you a sense of well-being, which boosts your immune system. They also do work to remove contaminants, particularly VOCs, from the air, so they can be very helpful to a healthy work environment. Promoting physical activity for your employees, for yourself, we'll do the same. And getting sleep. Sleep is very important. When you are sleep deprived, it will really creates stress hormones like cortisol, and that cortisol can really suppress your immune system. So a good night's sleep is very important to your immune system. And last but not least, very important, stay hydrated. Staying hydrated helps the body's naturally eliminate toxins and other bacteria that may cause illness. So drink water, lots of it. And I'm going to turn it over to Joe one more time, just to give us a summary.
Sure. Yeah, and I actually was able to bring my plants from the office to my home office, so the benefits continue. In conclusion, I think it's very important to remind everyone that there is no real silver bullet for controlling the spread of airborne pathogens. I mean, that's why social distancing is so effective. If there isn't another person to spread it to, then it doesn't spread. That's the best that we can do. But the HVAC systems can help. I encourage design teams to sort of assess every project and determine what level of mitigation makes sense. What are our performance goals for indoor air quality? And then take those performance goals and tailor the solutions that you offer to the building type, to the space types, how the spaces are being utilized, and to the type of HVAC system that you are implementing, whether it's a VRF system or a VAV system. There are going to be different solutions for different system types, and it's important to evaluate that. But we think that, if you apply these measures that we've included, whether alone or preferably in combination, it allows for architects and engineers to improve the quality of the indoor air environment for their projects. And the next two slides really just show some ideas, right? This is really just listing out all of the different things and looking at office space versus residential space, and where does it make sense to do one and where does it not make sense to do another. And it includes the DOS systems, UVC lighting, obviously increased air filtration is something that we would recommend everywhere. But using systems or adding a wet stack for distributed hand washing stations, I think that's something we're likely to see in an office building, but perhaps in a residential application, it's not as appropriate. The idea of using relative humidity and temperature and maintaining tight controls, I think that is going to be a critical application that we're going to have to see everywhere. And disabling demand controlled ventilation, really looking into how we're controlling the buildings and what is most appropriate and what provides the most flexibility. And finally, as a note, as Roger mentioned earlier, ASHRAE has spent a considerable amount of time consolidating a lot of their both new resources and resources that they developed years and years ago when it comes to the spread of airborne pathogens. So I would recommend everyone checking out the ASHRAE website, go to their technical resources page. There is more information than you could probably read in a week if you are very interested in getting down into the scientific details. So hopefully we were able to provide you with a pretty good summary of that. And I think with that, we will open it up to questions.
Yeah, and I will say we run a little bit longer than we thought, so we can answer a few questions, and any questions that we don't get to today, we will collect them all. We will put answers to them in writing, and we will send out another email, and in that email will be the Q&A with the answers, but also a link to the video for this presentation if you want to watch it again or share it with a friend. So we do appreciate you attending, and I'm gonna go over to the notes section here and see if we have any questions. Emily, I don't know if you're on the line, but I haven't seen the questions come through yet.
Oh, I can see a few, Roger. I'll take a stab. There's a handful here. I think the first one that I had seen come up at the beginning of the presentation was, how do you cope with shared spaces with limited access to fresh air? And that's a great question. And I think the earlier slide in the presentation that Roger showed of the restaurant highlights almost precisely that application. So when you really can't do a lot of dilution air within a space, you have to look at when you have these shared spaces with limited access to fresh air, you really need to look at, okay, is it a recirculating? Am I recirculating only within this space? If the answer is yes, then filtration ends up being a very critical application. But also looking at, in-duct UVGI, the photocatalytic oxidation, and the bipolar ionization, when you have spaces like that, that can be very useful. There's another question here about in a crowded office building lobby with screening queues, how should airflow be configured for maximum safety? That's a great question, because that is going to be absolutely a real world environment that we are going to have to deal with. I think the traditional idea of doing mixing ventilation systems, whether that's an overhead VAV system, fan coils, even VRF fan coils for that nature, they utilize mixing ventilation, which essentially, unless you're doing an extensive amount of filtration within that space, you're just mixing up all of the dirty air with the clean air. So I think you're going to start to see applications like displacement ventilation, where air is coming in from a low level, pushing up, stratifying the air, and taking the contaminants in the breathing zone up and away from people. I think that's going to be a strategy that is utilized much more in the future.
Yeah,
and
Joe,
finally, yeah, go ahead.
I was going to say, I saw another question here. Does the makeup air unit be a better alternative to air handling units, since we don't recirculate the air and we don't extract the return? Yeah, and I think, kind of Joe touched on this earlier, but if you have sort of a sort of older air handling unit that is recirculating, a mixing type VAV, it is a challenge to either filter that air or to apply a UV technology to try to disinfect that air, because that air is passing directly from the return, mixing, and coming back to the supply. So mitigation strategies are important. However, if you do have a DOAS unit, and that DOAS unit either has the ability to operate with the wheel disengaged, an energy wheel disengaged, or has been fitted with bypass, I think that's the best type of system if you have a major concern about infection, because again, you are literally all the air that is being delivered to the space is coming from the outdoors, and you are not re-entraining any of that air back into the supply airstream. Okay, Joe, did you have a?
Yeah, I think there was one extra question, so I know we're 4 minutes past time, but we might as well go ahead and answer the last one here. There was a question about are there any recognized sensors and devices which can measure or detect the air quality within a space? The answer to that is absolutely yes. Most of the manufacturers who are providing these UVGI systems, the photocatalytic systems, the bipolar ionization systems, all include a fairly comprehensive controls package that does active monitoring. And that's very critical, and I think will be critical moving forward, is that not only are we applying these technologies, but are we validating the results? So the answer is yes, that there are sensors out there. Now, is there a SARS-CoV-2 sensor? Not yet. Viruses are very difficult to monitor because of their size. But I think that you're going to see, more sensors coming onto the market that have a higher granularity.
Okay. All right, and if any other questions do come through, again, we will make sure we capture them, answer them, and recirculate them to all attendees. And I think I'd like to close by thanking everybody for showing up today, and also to let everybody know that 2 weeks from today, same time, we will have our next session, session number 5, which will be a discussion about using direct current DC power microgrids in office spaces. That discussion will be led by our own Craig Burton and Kulai Salitra, and it will be a great show. So please look for it. A registration announcement should come out sometime next week, but hope to see you again in 2 weeks. Thank you very much, and have a great day.